problem, but you know, it's been solved, of course. So we did solve it. So we did show what the solution is. It was pretty likely that in a room full of 30 people, in a room full of 30 people, there'll be at least one shared birthday. And you could probably guess also that the more people there are in the room, the bigger this probability is going to go up. So. All right, so that's the birthday problem. So I figured it'd be good to do that one. So I know the book does it. I figured it'd be good if I did it as well. Now I want to do another example with this formula. I mean, the book does mention it. I don't remember how much they go into it. I figured it wouldn't hurt to do another one. So let's suppose now we're tossing a two-sided fair coin, and with tossing it 3 times consecutively. I mean, what's nice about this is we can actually get the sample space. In other words, we can list all the outcomes. We can list all of them. Okay? And that's what I'm using this tree diagram for. Remember, you start at some point and you draw a branch for each outcome. So the first one, you have 8 heads or tails from the coin being tossed the first time. Then from each outcome, you toss the coin the second time and you get heads or tails. If you got tails, you would get heads or tails as well. And then from each of these outcomes, this is from the second toss, or that second category as the book says it. You toss the coin the third time and you can get heads or tails. Heads or tails. Heads or tails. Heads or tails. And you can get each outcome by starting at the top and getting down to the bottom. The path you take is an outcome. So if we start here, you get heads. The coin lands on heads up. The second coin lands heads up. The third time we toss it, it lands heads up. So that's one outcome. For the next outcome, okay, the next one, yeah, the coin lands heads up. The second time it lands heads up. The third time it lands tails up. So we have H, H, then T. And we keep on doing this. So for another outcome would be heads, then tails, then heads. And you can keep doing this to get all the outcomes. I mean, what's nice here is there's not too many. There's only 8, which is really nice. But I figured it'd be good to go through this because remember, you're not always going to be able to list every outcome. I mean, what if you were rolling a die 3 times? The total number of outcomes then, by the basic counting rule, because each time there are 6 possibilities, you would have 6 cubed, which is over 200 items, 200 outcomes. I don't know about you, but I don't want to list 200 outcomes. So here I figured it'd be good to do this example. All right. So with that in mind, let's consider this one. Let's find the probability of these events occur. The coin lands heads up exactly 3 times. And then we'll find the probability that the coin lands heads up at least 1 time. Okay? So we're going to find out these probabilities. Okay. I mean, again, it's a little bit easier. So I'm going to use 2 methods. One by just looking at the sample space. The other one I'm going to use that formula just to illustrate it. Okay. So we want the probability that the coin lands heads up exactly 3 times. Well, looking at the sample space, there's only one way, only one outcome where that happens, right? Here. So because of that, the probability that the coin lands heads up exactly 3 times, right? That's 1 out of 8. 1 out of 8. That's what we get here. What about the probability that the coin lands heads up at least once? Well, at least means one time or more. One time or more. Okay, when does that happen? Well, if we go, I listed the outcomes here on the sample space. We have 1, 2, 3, 4, 5, 6, 7. So 7 out of 8. Okay? So that's what happens here. There's 7 out of 8. Remember, for at least once means once or more. We didn't say exactly once, we said at least once. Now, the other way to get it is, going to the next slide, the other way to obtain it is we can see the complement. That is, we can use that formula 1 minus. Okay, well, instead of finding the probability of at least once, we could find the probability of it never happening and then subtract it from 1. So in other words, we could find the probability of it never landing heads up and then do 1 minus that. So never landing heads up, in this case, never landing heads up, well, we went back to our sample space. Only one time when it happens, when you have all tails. And that's 1 out of 8. The probability of the coin never landing heads up is 1 out of 8. So we do 1 minus, and that gives us the probability of at least. Heads up at least once. Well, at least once heads up. Maybe that would be better to say. And of course, from there, we get 1 minus 1 over 8, which is 7 over 8. So that's what we get. Okay. I know it wasn't really much of an example, but well, I just wanted to make sure at least that I at least gave one example using this kind of formula. I just thought it'd be good practice. I think it is useful because generally it's a lot easier to determine the probability of something never happening than it is to determine it happens at least once. I thought it'd be good to do that. Okay, any questions on that? Remember, I can't see the chat, so if you have a question, use the hands up feature. Okay. So we looked at permutations, right? Remember, with permutations, okay, there the order mattered and selection was made without replacement. So the order mattered. In permutations, the order mattered, and selection was made without replacement. Combinations is what you get a combination instead when the order doesn't matter and it's made without replacement. So in other words, what happens if order does not matter and repetition is not allowed either? Then we have what's called combinations. Fixing this. Order does not matter. There we go. That's what happens here. And then we have a combination. And a combination, again, is without replacement, so no repetition, and it does not matter. N and R are the same, so you're making a selection of size R, or you could think of as forming a list of size R from N choices. And again, the order does not matter, and there's no repetition. Well, it turns out that we get this formula. As you can see, it's the same as P of NR, except we're dividing by R factorial as well. That just handles the order. And you could use that Desmos calculator. I'm not sure if you saw it or not, but next to that NPR thing, there was this. And that's what this is. you can do that using Desmos calculator. I'm not sure if I would think the other TI graphing calculators have it. I'm pretty sure they do. But you can always use the factorial calculations as well. You can always use that if necessary. That's combination.